Hello everyone. In this part, we will look into few of the storage technologies that are used in various secondary storage devices that we use. The reading for this part would be from chapter 12 from the Dinosaur book. Although there are a few things that I'll be explaining in this part which are not necessarily in the book, but the material that we cover in the slide should be enough to understand the concepts. So, in this part, we will look into three most popular categories uh, of storage technologies that are in use now. So, the first technology is tapes, and then we'll look into magnetic disks, and then we'll conclude our discussion with flash memory. Okay. So, tapes are the traditional form of storage, which was like the first large scale and commercial secondary storage that was available to general public. So the tapes are, as you can imagine, if you ever like if you know about cassette tapes where you store audio files on a cassette tape, it's similar to that similar technique we use to store data on magnetic tapes. And these tapes are of low cost and they are very high reliability. They have very high reliability because they don't have any mechanical parts, active mechanical parts themselves. And once you write the data stays there, and the data stays there for quite some time, like almost for like for entire lifetime. The one of the main disadvantage of tapes is they have very slow access time because almost all the reads are sequential. So tape, as you can imagine, it's a sequence. It's a long ribbon, and then we store data by writing magnetic particles onto that magnetic ribbon, right? So accessing data depends on where the data is located relative to the current tape position. So if the data is at the last sector, then we may need to like rotate the tape. We may need to go to the end of tape, which takes lot of time. So on an average, the access time of tapes is very slow. So on an average, you can say that it's around the fastest tape would be around like 30 MB per second. Although recently there are some techniques which have like very high access rate. So although tapes are very old, they are still used. We still use them, and they're mainly used to create backups. Okay, for instance, Purdue uses tapes for backups. So these are very nice material or like very nice technology to create permanent backups of certain data, which we don't need to access every now and then. So if we have some data that we just want to archive and we don't have a requirement of accessing it at a regular basis, then it's better to store all the data on a tape and then store the tape somewhere else and then have a label on those tapes so that when you want to access the data, you can take the tape, put it into a tape drive and read the data back. And in fact, actually, this is used in companies, it's used by Purdue, and most of the organizations use tape to create a permanent backup of the data. The next technology we'll look into are magnetic disks. So magnetic disks are quite popular. These were de facto standard for storage in most of the systems, on laptops, on desktop systems, servers everywhere. However, they are slowly being replaced by flash storage, but magnetic disks had their time. And they have relatively high access rate, around 150 MB per second. However, this rate improves, also improved with different technology. A disadvantage of magnetic disk compared to tapes is their high failure rate because magnetic disks themselves has very active components in them. So of course, when you have like too many active components, the chances of failure is very high. And furthermore, the more you use magnetic disk, there is high chance of failure. So failure is kind of inversely proportional to the usage. So let's take a deep dive into magnetic disks and see how they work and what are the components that affect their access time and how exactly an access made to a magnetic disk will be satisfied. So magnetic disk, a picture of magnetic disk as shown on the slide. So it has many active components, and magnetic disk is usually connected to the system by using a SCSI connector, SCSI. So here, uh, all the data requests come to the magnetic disk from the operating system through the connector, and then magnetic disk store data onto platters. These are just concentric circular magnetic disks, and there is a spindle that rotates these platters, and furthermore there will be an arm or head which actually reads the data from surface of the platters. Okay, and if we take a deep look into the platters, platters are arranged in a stacked manner, so they are arranged on top of each other, and the head, which is like the read write head, covers both the surfaces of a platter, and for each platter you have upper surface and lower surface, and the surface of each platter is divided into concentric tracks. Okay, and each track is further divided into a sector. Okay, and the intersection of a sector and the track, that's also called a block. So that is the unit of read or write from a disk. Okay, and all the tracks uh, from a of a disk, they form a cylinder. Okay, this like track one of all the platters of all the surfaces, they form a cylinder. And let's see what happens when we try to access certain data from magnetic disks. Okay, as we know, surfaces are organized into tracks now, and we also know that disk access happens in granularity of sectors or blocks, which are usually of size 512 kb or 4 kb, or like 4, yeah, 512 kb. And then this, actually it's 512 bytes. That's some typo there. It's 512 bytes. And the IO interface, I mean, this interface is called block IO interface because the access granularity is in terms of blocks. Now, let's say we have the disk head, the read head is at the track 3. Now, what happens when we, the disk usually rotates counterclockwise. So there are two movements that can happen in magnetic disk, right? One, we can rotate the platters, we can rotate the disk, or the other one is we can move the read head to different tracks. We can actually move the read head towards the center track, or we can move the read head out to the outermost track. So the movement of read head happens laterally, whereas the movement of disk happens in a counterclockwise manner. Now, when we have to, let's say we want to read blue sector. So here, the read head is at the correct position. It's just at the right position to read blue sector. And then when we want to read blue sector, we just uh, we activate the read head. At the same time, we rotate the disk in an in the counterclockwise, so that the read head reads all the data corresponding to that blue sector. Okay. Then after we read the blue sector, the position of read head would be just after the blue sector. Now, let's say now the next request comes. In this request, let's say we want to read red sector. Okay. In this case, first the read head will seek to this track containing red head. So here read head is at the track of blue sector. So now the read head will be moved backwards so that it will align itself to the track of the red sector. And then we rotate the disk in a counterclockwise so that the read head is just before the red sector. Finally, we read the red sector and we transmit the data that we read to the operating system that made the request. Okay. So on real disks, there are usually 1 to 8 platters. So each platter has two surfaces. So there are 2 to 16 surfaces for data. And there are usually 10 to 1,000 tracks per surface. And of course, there will be same number of cylinders because all the tracks of all same track of all the cylinders of all the platters form a cylinder. So you'll have same number of cylinders as the number of tracks. And number of sectors per track is 200 to 1,000. So that translates to 100 to 500 KB. The number of bytes per sector is usually 512, as I mentioned before. However, in recent disk, you can actually choose the size of the sector to be. In the next part, we will look into what constitutes, like what are the delay elements of disk access and how disk can fail, like if at all, if it fails, what are the things that make the failure happen more frequently. Thank you.